our concept of dimension is also relevant to our study of directed graphs. I want to now introduce the language of the Betti numbers of a directed graph. The Betti numbers are numbers we've seen before, but we didn't give them this name. So there are two Betti numbers of a directed graph. The zeroth Betti number, which is denoted by h sub 0 of g, is the number of connected components. Remember, this is sort of the number of islands in the directed graph. And the first Betti number, which is denoted by h1 of g, is the circuit rank of the directed graph. Remember, this is the minimum number of arrows you need to purge from the graph in order to break all of the cycles. And also, I want everyone to remember that in our very second lesson, we learned the concept of Euler Characteristic. The Euler Characteristic of a directed graph is this really simple number, the number of nodes minus the number of arrows. What we're about to find out is this concept of dimension relates all of these numbers. And this is kind of cool because this is how linear algebra helps us study certain interesting things. So let's say that we're studying the incidence matrix A of a directed graph G. So remember, the incidence matrix will be M by N, where M is the number of nodes and N is the number of arrows. So it's worth asking oneself, well, what are the dimensions of the four fundamental subspaces? Remember, to calculate dimension, you must find a basis and count the number of vectors. Well, when we looked at the dimension, or when we looked at the null space of an incidence matrix, remember what we did. This was from the previous lecture. We purged the minimum number of arrows necessary to break the cycles, and then we used those arrows to construct one basis vector each. What that's telling us is that the dimension of the null space is equal to h1 of g. That is the circuit rank. That's pretty interesting. So the dimension of the null space is the circuit rank. On the other hand, think about how we found a basis for the left null space. We looked at each connected component and figured out the classification vectors on the nodes. Each connected component contributed exactly one basis vector to the left null space, which means that the dimension of the left null space is h0 of g. That's the number of connected components. That's pretty interesting as well. And remember, we can use the rank nullity theorem to figure out the other dimensions. We know that the dimension of the null space plus the dimension of the row space should equal the number of columns. So the dimension of the row space should be n minus h1 of g, the circuit rank. And over here, the dimension of the column space should add to the dimension of the left null space to be the number of rows. So the dimension of the column space is the number of rows, which is the number of nodes in the directed graph, minus h0, which is the number of connected components. But also, remember, the dimension of the column space is always the same as the dimension of the row space because that's the rank of the matrix. So this gives us an equality. N minus h1, so the number of arrows minus h1, must be the same as m minus h0, which is the number of nodes minus h0. And when you rearrange this equation, you get an amazing result. You get the Euler characteristic is equal to h0 minus h1. The way we're getting this is we're moving h0 from the right-hand side here over to the left-hand side, and we're moving n, the number of arrows, over to the right-hand side. So the Euler characteristic, which is very simple to calculate, this is the number of nodes minus the number of arrows, is always the same as the number of connected components minus the circuit rank. So this is a very surprising result, and what's cool about all this is we're doing this using pure linear algebra. Let's see this in action. So generally, the way I like to think of the utility of this theorem is that circuit rank's pretty hard to calculate. If you give me just some directed graph, figuring out the minimum number of arrows you need to purge to break the cycles might be a little tricky. On the other hand, if we're in a situation where we know the number of connected components, what this theorem is telling us is that can help us figure out the circuit rank. So here we have an example of a directed graph. The number of nodes is 5, and the number of arrows is 6. So I can calculate the Euler characteristic. The Euler characteristic is 5 minus 6, which is negative 1. It's also, in this example, not terribly difficult to see that the number of connected components, H0, is equal to 2. Well, this equation is now saying I don't have to worry too much about calculating the circuit rank H1 because I can solve for H1 here. And H1 should end up being 3 because 2 minus 3 is equal to negative 1. So this allows me to circumvent the circuit rank calculation by knowing the Euler characteristic and being able to see what the number of connected components is, H0.